Hello there, Mr. Sutton here, bringing you this lesson on vectors. In this one, we're going to apply the concept of motion to vectors. And, for example, we're going to find the speed of an object not moving in a straight line. Let's talk a little bit about vectors. Now, you might remember doing some crazy things like adding them and dot products and cross products, but vectors AP style mainly involve just putting parametric equations together into a component form. So you'll get these parametric equations like x of t and y of t, and if you want to write a vector for them, you basically stick them together, so x of t comma y of t. And for vectors, we typically use these angle brackets. You might have seen these before. You can also use parentheses, but I think it's kind of weird because you might mix it up with just like a regular point. All right, so let's do a problem involving vectors. Let's say we have a bat whose position is given parametrically by this x of t and y of t equation. We want the position vector, which we'll call s of t, and the bat's position at time 5. Pause the video and see if you can intuit, based off of what we wrote up here, what you actually need to do. So all we really have to do for the position vector, since we already know the x and the y coordinates, is just to put those parametric pieces together into this component form. So for s of t, we can write 3t squared, that was x of t, comma 2t cubed. And the funny part is, since they defined x of t and y of t, if this were a free response, you could have just written x of t comma y of t and gotten credit. But this is a little bit more explicit. Now we want to find the bat's position at time 5, so basically s of 5. Now if you're finding a regular point, you can actually just use regular parentheses if you want to. So we've basically just got to plug this into our two coordinates here. 3 times 5 squared and comma 2 times 5 cubed. If you wanted to simplify it unnecessarily, you could write, let's see, 3 times 25 is 75, comma 2 times 125, that's 250. For this next example, we have the location of an airplane at a fixed height given by this position vector right here. We want the velocity and acceleration vectors of the airplane at t equals pi over 2. So we need to, in general, find the velocity and position vectors in terms of t. Then we need to actually plug in pi over 2 to get some actual numbers in the vectors. So we'll do the velocity vector first. In general, you're going to be creating vectors and finding velocity and acceleration for x and y separately. So my velocity vector, that's going to be x prime of t, comma y prime of t, just the first derivative of motion here. So pause the video and see if you can come up with a general velocity vector and then plug in pi over 2. All right, so treating the x and the y separately, derivative of sine of 2t, that's going to be 2 cosine of 2t. And then derivative of 2 sine of t, that's going to be also, well, actually just 2 cosine of t. There's no 2t inside, so they're pretty similar but not the same. And now we need v of pi over 2. So that's going to be 2 times the cosine of 2 times pi over 2. 2 cosine of pi, basically. Cosine of pi is -1, so this is -2 for that first vector, for that first component. And then over here, cosine of pi over 2 is just 0, so 2 times that is still 0. So this is giving us our velocity vector. So this is telling us at time pi over 2, we're moving a little bit left and moving nothing forward and back or up and down, whatever you want to use for that y coordinate. All right, pause the video again and see if you can figure out the acceleration vector. So for acceleration, we need x double prime of t and y double prime of t. So let's go ahead now and write that out. That's going to be, let's see, using our velocity vector here and just taking one more prime on these, we're going to have -4 sine of 2t. And over here, this is going to be -2 sine of t. Now let's go ahead and plug in pi over 2 to both of those expressions. So let's see here. This is going to be sine of pi, which is 0, so that zeroes out that whole first component. Over here, sine of pi over 2 is 1, so this is just -2 then. On this example, we have a fruit fly moving with a velocity vector given as follows here. We want to know when this fruit fly is at rest. So you might remember with parametrics, figuring out times that we had horizontal versus vertical tangent lines, where one of these things had to be 0 and the other was not supposed to be 0. Well, with that rest, we're trying to figure out where x prime and y prime are both 0 at the same time. So basically figure out when one of them is 0 and then plug those values in to see if they also make the other one 0. Pause the video and give that a shot. Alright, so it's up to you whether you use x prime or y prime initially. I'm going to start with x prime, which is this 4t minus 12t squared expression. And I'm just going to see when this equals 0. So I can solve this without a calculator. We'll just factor out a 4t, leaves me with 1 minus 3t. And that gives me t values. For the 4t, we have t equals 0. And for this 1 minus 3t, let's see, subtract 1, divide by negative 3, we have positive 1/3. So these are times when the left-right motion is 0, the x prime is 0. But I need to figure out if the y prime is also 0 at these times. So let me figure out what y prime is. They actually gave it to us here. It's this 2t minus t squared expression. Now, if they didn't give us the velocity vector, if they gave us position, you'd have to find these derivatives before you could do any of this. But we started with velocity. So now let's see if y prime of 0 also equals 0. So that's 2 times 0 minus 0 squared. That's definitely 0. Since x and y prime of 0 are both 0, we can conclude that the fruit fly is at rest at time 0. But we still need to test out this 1/3 here. So y prime of 1/3, that's going to be 2/3 minus 1/9. And let's see here, that's 6/9 minus 1/9 is 5/9. Really, the most important piece is this does not equal 0. So that means that we've got some up-down motion, so the fruit fly then is not at rest at time 1/3. For this next one, we have Wario moving such that his dx over t is given by this e to the cosine of ln expression. And here's his y prime right here, square root of 13t. We want, at time 2, his position is 7, 10. We want to know where he is at time 8, and this is a calculator question. So you've done all this kind of stuff before on a single axis. You had that particle moving on the x-axis, you had an initial value, you had the derivative of x, and we just needed to use fundamental theorem to find the new value. Well, we're just going to use FTC here for x and y individually. So for example, to find the new x value, x of 8, that's going to be your initial x value of 7, plus we need an integral. We need to basically get the total change between times 2 and 8 of x. So that's going to be an integral from 2 to 8 of whatever our derivative of x is, x prime here. Now, since they've already defined x prime for me up here, I just have to write x prime of t dt. I don't have to copy the whole thing or even take the derivative and figure out what it is, right? They already gave it to me. So let's plug this in the calculator. So here I am on my calculator in my y equals, and one thing it's very helpful to do, whenever they give you these expressions and you know it's a calculator question, you should generally immediately enter these in your y equals because you know you're going to be using them. So y1, I've got my dx over dt. In y2, because I know I'm going to need it, I've entered the dy over dt. And now let me quit out of there and let me do math 9. Actually, first I need to do 7 plus, and then math 9, integral from 2 to 8 of, and I've stored x prime as y1, so alpha trace y1, and then dx, all comes out to about 13.5697, so we'll call that 570. So pause the video and see if you can figure out the new y value at time 8. All right, so for y of 8, we need the old y value of 10. That was our y value at time 2, plus an integral again from 2 to 8. And this time we've got y prime of t dt. Calculator time. So this time on my calculator, I'm doing 10 plus integral from 2 to 8 of y2, because that's where I stored this y prime here. And that's going to come out to 57.591. So putting it all together, we've got the point 13.570, comma, 57.591. For this problem, we have a lizard moving the xy plane between 0 and 2 pi time. And here are our motion functions, x of t and y of t. We want to know the speed of the lizard at time 1. Now remember, speed and velocity are not the same thing. Recall that speed's the absolute value of velocity. And this is a little bit tricky when we're dealing with a parametric set of equations. If we think about this in terms of vectors, you might remember that the absolute value of a vector, the distance from 0 with a vector, is really going to be found by taking the Pythagorean theorem of A and B. So applying that now to vectors and the two-dimensional motion here, speed is going to be the square root of x prime of t squared plus y prime of t squared, since that's your A and B components in a vector for velocity. So applying that to this problem, we essentially want all of this stuff with 1 plugged in for the t value here. Now, the good news is that if you're just taking the derivative at a single value, you don't have to write out the explicit function. You can calculate derivative at a single value without writing out the formula. So take a moment, pause the video, and plug this in your calculator. In order to plug all this in without actually figuring out the derivative formula, I'll start by putting these x and y components in my y equals here. Here's what I've done back on the main screen with those functions. I'm taking my derivative of y1, which was my x here, so that's x prime, evaluated at 1, and then squared that. Done the same with y2, which was my y prime. And all of that is going to come out to about 3.844 if you've done that correctly. And that unit is going to be feet per second because this is speed. For this next problem, we're taking that lizard from the last example and basically asking the total distance it traveled between time 0 and 2 pi. So recall for total distance, we're talking about the integral of the absolute value of velocity, basically integral of speed over some time period. So in this case, since speed is that square root of x prime squared plus y prime squared, we're taking the integral of what you just did for speed, and that gives us total distance. So on this problem, we're going to take the integral of x prime of t squared plus y prime of t squared. The problem is we don't have the x and the y prime. On the last problem, we took the derivative at a single value, so we didn't need to figure out what they were. This problem, we have to actually explicitly write the formula for these derivatives in order to use it in a function or an equation. So take a moment to find those derivatives. So for x prime, we're using the product rule. We've got a box and ribbon here with e to the t and sine of t, whose derivatives are e to the t and cosine of t. Using my ribbon, I've got e to the t sine of t plus e to the t cosine of t. For y prime, pretty much the same deal, but with e to the t and cosine of t. Those derivatives are e to the t and negative sine of t. Using my ribbon, I've got e to the t cosine of t minus e to the t sine of t. So the good news is now that I've defined x prime and y prime, I can pretty much just write this formula with 0 and 2 pi for my limits of integration, and everything else is going to be exactly the same because of how I defined these. Let's take a moment to do this on the calculator. First thing I'm going to do in my calculator, as always, to make my life easier, in y3 this time, because I already used up y1 and y2 for the motion functions, y3, I've got my x prime. In y4, I've got my y prime. And now let me quit to the main screen. And here's what my setup looks like on this one. Math 9, integral from 0 to 2 pi. And now, since I'm just squaring the general functions, I can just do y3 squared and y4 squared inside there. Enter. And that comes out to 755.885. And units, that's going to be feet because this was total distance. Now, one other interesting thing to note is that we basically found the arc length of the motion function over an interval, if you remember what we did on that last lesson. So that's it for this one. You might say I gotta run. Till next time, Mr. Sutton signing off.